So I'm going to talk about more planetary-focused stuff, in particular thermal convection in icy moons ocean that was introduced very nicely by Krista yesterday, and particularly focusing on the influence of heterogeneous heating through tidal heating. I'm going to go very fast through the introduction. Again, this was outlined yesterday. I'm going to focus mostly on an icy moon, which is called Europa, which is a moon of Jupiter, roughly the size of the Earth's moon, which is covered with this bright ice layer with nice geological features. And from various observations, including the detection of an induced magnetic field, we know that there is probably a global liquid and salty ocean that lies beneath this ice crust. We also know from interior models that it's probably a differentiated body, in particular with a rocky mantle that lies beneath the ocean and in direct contact with the ocean. So for most observations for icy moons, it allows us to quite constrain the properties of the ice shell and the composition of the ice shell, but we really have a lack of observational constraints on the dynamics and the features of the ocean and the ocean circulation. So it's really important from the fluid dynamics perspective to try to propose better models of this circulation. So I've listed here some kind of global key questions. As Krista pointed out yesterday, we don't really know what process drive the flow in these oceans, or at least what are the dominant processes, how do they organize, how do they compete with each other. So we're talking about mostly thermally driven flows, salinity-driven flows, or mechanical forcings that Michael is going to talk to us about in the future. Today, I'm focusing mostly on thermally driven flows, but of course, bear in mind that this is only one possibility. Okay. What does the circulation look like? And in particular, how does it organize at large scale? How this circulation is able to transport heat and materials from the seafloor up to the ice-ocean boundary. And of course, this is particularly important for all questions related to habitability. And if there is any, what is the dynamical coupling between this ocean and the ice crust? And of course, it's particularly timely to address these type of questions because we have two missions that are going to arrive at the Jovian system in the 2030s. Europa Clipper, which is a NASA-funded mission, and JUICE, which is a NASA mission. Okay, so if we want to be able to interpret observations as best as we can, or even to target strategic observables on these moons, we need better forward models, including better fluid dynamics models. So today I'm going to be concerned mostly with the effect of tidal heating. So what do I mean by that? Europa revolves around Jupiter on an eccentric orbit. And so the effect of this eccentricity is that the tidal forces and the resulting tidal bulge is going to vary as Europa revolves around Jupiter. And so you can see, as shown on this animation here, that this is going to generate some heating in the interior solid layers of Europa, particularly the rocky mantle and the ice shell. And so we worked with Carver Bierson, who at the time was a postdoc at Arizona State University, on understanding what would be the heating pattern that would result from tidal heating in Europa's mantle. And so using a three-dimensional model, assuming that Europa is a multi-layered body, and again, making assumptions about the rheology of this body, you can get a prediction for this tidal heating, and in particular for the heat flux that you would get at the top of the mantle at the seafloor, basically underneath the ocean. And this is what you obtain, and this is consistent with previous studies that I've listed here that I've been looking at that. So there are two important points here. The first one is that it's a strongly heterogeneous heating. It's higher at the poles, lower on average at the equator, and you have this nice order 2 pattern at the equator. The second important point is that the amplitude of the heat flux variations are of the same order as the mean heat flux. So we're not talking about small heterogeneities. This is a large heterogeneity. In the following of the talk, I'm going to use this parameter Q star to quantify the amplitude of the heating anomaly. It's basically going to be the peak-to-peak heat flux difference divided by the average heat flux. So for tidal heating, this is of order 1. Okay?
And is there some convergence in that pattern? Is that just your study with Bierson?
No, it's like the previous study, Sautin, Tobier. There's a consensus of on the pattern. The main debate is on the amplitude of the average tidal heating. I'm going to discuss that in the following. But essentially, the pattern is really dominated by two spherical harmonics. So first of all, the degree 2, order 0, axisymmetric pattern, just higher heat flux at the poles, and then this degree 2, order 2 variations in longitude. Okay, and this is really what dominates the effect on the dynamics that I'm going to describe later. So yeah, as I said, the uncertainty is on the average amplitude, if you want, of this tidal heating in the mantle, and in particular for what I'm going to describe, we don't really know how it compares relatively to radiogenic heating in the mantle. And the problem is that radiogenic heating is supposed to be homogeneous, right? So if tidal heating is negligible compared to radiogenic heating, you're just heating the ocean homogeneously. Whereas if it's dominant, then you're in another configuration where the heterogeneity could have a large impact on the ocean circulation. So just to illustrate some of the state-of-the-art models that we have for heating in Europa as mantle, I just wanted to briefly mention this study here by Behunkova and collaborators, where they looked at the thermal evolution of Europa with the goal to investigate when magmatism could occur in Europa as mantle. I'm not going to go into the discussing magmatism. I just wanted you to look at these two plots showing the power as a function of time. And I've highlighted two curves. The yellow one is radiogenic heating, and the orange one is tidal heating. And they considered two scenarios, a scenario where there is a low radiogenic content in the mantle, and a scenario where there is a high radiogenic content. And so what I just wanted to point out here in this specific model is that at the end of Europa's evolution, after 4.2 billion years, tidal heating represents roughly 40% of radiogenic heating. So that's one model among others, but this is just to say that it could be as large as radiogenic heating, and in some scenarios, it could also exceed it.
Does this model assume that the mantle is convecting?
I don't think so. No. And so it's really investigating the melting in the mantle. But the interesting point is that in this high radiogenic content scenario, even when there is melting in the present era, you can see that the pattern, so this is the heating variations that they get at the top of the mantle. You can see that despite these melting patterns, you still get the large-scale heating patterns that is apparent from these heating variations. Okay. So the point that I want to make here is that, okay, we don't really know how heterogeneous is the heat flux. If radiogenic heating is important, then it should be a homogeneous heat flux, so Q star close to 0. If tidal heating is dominant, Q star could reach values of order 1. And the three main questions that we wanted to address in this study was to understand, well, if you're considering this type of heating pattern, what would be its impact on the large-scale variation on the large-scale circulation in Europa's ocean? Second question, if you have large-scale thermal anomalies, how are they transposed up to the ice-ocean boundary? Are they erased by the convection, or can they make their way to the top of the ocean? And three, if you have heating variations beneath the ice, can they be strong enough to affect the equilibrium of the ice crust? And this is, of course, with the idea that the ultimate goal is to try to find a way to compare this with observations, which again are only indirect. So because we're trying to make cross connections here, as John mentioned yesterday, the effect of a heterogeneous heating pattern on rotating convection has been looked at because it's relevant also for the Earth's outer core. So the reason for this is that from seismic data, we know that there might be heterogeneities at the base of the mantle, thermal or chemical heterogeneities. And so the heat flux at the core mantle boundary, CMB, could be strongly heterogeneous. And this is an example of heat flux variations at the CMB inferred from tomographic data that were published in this study by Mound and collaborators. Okay, and you can see, interestingly, that you have the same kind of order 2 variations in the heat flux. Not related to the physical phenomena at play, but just a similar large-scale pattern. So I'm not going to cover, of course, all the literature on outer core convection with an imposed heterogeneous heat flux, but I wanted to mention in particular this study by Dietrich and collaborators in 2016, where they looked at rotating convection with internal heating and an imposed heterogeneous heat flux on the outer boundary of the sphere. And in particular, they look really in detail at the hydrodynamics of the system, and they explain how temperature variations in longitude can induce geostrophic radial flows. So I'm just going to explain this, walk us through this in this slide. So to show this, you can start from the Navier-Stokes equation, and we're going to seek a solution in the limit where the flow is assumed to be steady. We're going to be in the linear limit, so we neglect inertia, and we neglect also viscous effects. We're going to take the curl of this equation, so this gives you the vorticity equation, where we only have two parameters left, the Coriolis one and the buoyancy one. And then we're going to take the z component of this equation, so focus on the actual vorticity equation. And then we're going to average this equation vertically. So the vertical average is defined here. It's 1/2h, the integral from minus h to h, where h is the half height of this fluid column measured along the rotation axis. So we're basically looking for the geostrophic flow here. Okay, and so then from this, so that's the equation that you get. And here you see that you have the z average, the vertical average of the z derivative of the vertical component of the velocity. And so you can express this as the difference between the velocities, vertical velocity at the top and at the bottom of your fluid column. And using the fact that you have non-penetration of these sloping boundaries, you can express this as a function of the radial velocity, again, averaged vertically, which I call USE here, S being the cylindrical radius, not the spherical radius anymore. Okay? And so then if you put this back in your equation here, you get an expression for this geostrophic radial flow, US averaged over the depth. And what you get is that it depends on dt by d phi, where phi is longitude. So this basically tells you that the radial geostrophic flow will be induced by variations of the temperature in longitude. Okay, so it's a thermal wind balance here. So equatorial upwelling and downwelling will occur where the boundary temperature gradient is the largest. So to illustrate this, I'm taking here some of their results. So this is the setup. So we're looking at an equatorial slice. The heat flux, the imposed heterogeneity is basically a larger heat flux on one side and a smaller heat flux on the other side. So the temperature field that you get is the following: colder here, warmer here. Temperature gradient along longitude is highest, is largest here and here. And as a consequence, you get a downwelling here and an upwelling here. Okay, and if you look at the corresponding azimuthal circulation, you have this kind of loop that develops to close the circulation. And this is what is represented on this diagram on the left. So I forgot to say here that these visualizations here are in a so-called conductive regime. So the Rayleigh number is basically extremely small, much smaller than the critical Rayleigh number. So it's not, there's no radial convection occurring here. It's a conductive regime. And the amplitudes are so small that it's also a linear regime, if you want. Okay? So this is really to check the validity of this prediction in this regime. Okay? And then what they did is basically that they increased the Rayleigh number to incorporate little by little more nonlinearities. So again, they are showing slices, equatorial slices, temperature, azimuthal temperature gradient, and this is now the stream function. So if you want the radial flow, you take the derivative of the stream function along the longitude, and if you want the azimuthal flow, you take the derivative along radius, basically. So your downwelling is here, your upwelling is here. And then they increase the Rayleigh, and so the first thing that happened is that they switched to a regime that they call advective. So by this, they mean that advection, in particular of the temperature, becomes significant, but you're still subcritical to radial convection. There's no radial convection occurring in the system so far. And what they show is that basically as advection becomes significant, this downwelling becomes narrower and narrower, and the upwelling, conversely, becomes broader. Okay? And if you look, you can see this also on the temperature field or the azimuthal temperature gradient, where you can see that the downwelling is associated with a very narrow jet structure that goes inward. And the other important thing is that this kind of very narrow downwellings creates two regions in the outer core, a warmer region and a colder region over here. And finally, they increase further the Rayleigh number such that now we are supercritical with respect to radial convection. So now radial convection is superimposed to this sort of horizontally driven convection. Okay? And their main conclusion is that it doesn't really affect a lot this pattern. You can see that this inward jet still persists. One of their conclusions is that this kind of large-scale boundary-driven circulation is going to affect the properties of the radial convection. In particular, they show that the efficiency of the heat transfer is reduced, with the Nusselt number in that case being about half what you would get if you were to impose a homogeneous heat flux on the outer boundary. All right, so that's, yeah, yes?
The horizontal Rayleigh number is based on the azimuthal temperature gradient?
Yes, because it's a hemispherical pattern, so yes.
Rayleigh H is based on this horizontal gradient.
Yes.
And the critical Rayleigh is a critical Rayleigh that would be there
for radial convection with no heterogeneity. Yes. Yeah. Okay, and so this seems to indicate also that if you have a heterogeneity on the outer boundary, it could be able to reach the inner boundary. In other words, the inner core, which is interesting for geophysical applications because there's discussion about an asymmetry of the inner core, again, hinted by seismic data. However, there's been more recent studies, in particular by Davies and Mount, 2019, where, so I don't know why I put all of these figures. Let's just focus on this one, panel D. So again, it's the same kind of setup, spherical shell, rotating convection with an imposed pattern on the outer boundary, an imposed heat flux, heterogeneous heat flux. And what they show here is, so the temperature variations that they get at the inner boundary relative to the temperature variations that you get at the inner boundary in the case of homogeneous heating, okay? So basically, if it's equal to 1, it means that the temperature variations at the inner boundary are the same as in the case with homogeneous heating, so no effect of the heterogeneity. Because they wanted to basically address the question of, will this heterogeneity propagate and affect the inner boundary and so the inner core, right? And what they seem to find in the study, so they did a massive systematic study, and what they seem to find in particular is that as you reduce the Ekman number, it seems like the temperature variations that you get at the inner boundary just become the same as what you would get with a homogeneous heat flux on the outer boundary. So what they're arguing with this study is that for regimes relevant to core convection, it seems like these heterogeneities would not be able to propagate down to the inner core. Okay, so I've tried to find also data from laboratory experiments. So there's this experiment by Sumit and Olson in 1999, which consists in a rapidly rotating hemispherical shell. And so the interior is maintained as a lower temperature compared to the exterior of the hemisphere. It rotates at 200 RPM, so we're definitely in a regime where centrifugal buoyancy is dominant compared to the Earth gravity. And how they impose a heterogeneity is by placing some kind of rectangular heater on the boundary of this hemisphere. Okay? And this is what you would get from an equatorial slice. And this is a type of visualization of what they observe. So I forgot to say that, yeah, the Ekman number is typically 10 to the minus 6. They are in a strongly nonlinear regime, and the heterogeneity is really of large amplitude. Okay? And so this is a type of visualization where I think they inject fluorescent dye in the region where the heater is placed. And what they get is this type of spiraling jet that goes towards the interior and reaches eventually the inner boundary. And so this is a schematic of this circulation where you get this inward spiraling jet that separates a cold region from a warmer region. And so if you remember what I just talked about from the study by Dietrich, this is really reminiscent of this case where the downwellings become really confined to a narrow jet that eventually reaches the inner core. And then we have other types of experiments by Sau and Srinivasan, 19, which is in a bit of a different geometry. So this time it's cylindrical annulus. Again, rotating fast up to 300 RPM. Again, the inner cylinder is maintained at a lower temperature, and the sides are heated by nichrome wire heating elements. And they impose two types of patterns, so either hemicylindrical, so one side has a lower heat flux imposed, and the other side has a higher heat flux. And they also consider a twofold pattern, so higher heat flux, lower heat flux, higher heat flux, lower heat flux, which would be more relevant to what is observed from tomography data. Okay, and then they do PIV on a horizontal plane through this system. So this is an example of visualization that they get. So this is the heating pattern that they impose. So the green regions are subject to a lower heat flux compared to the orange region. Effectively, I think we're in a case where Q star is equal to 2, meaning that basically the green regions, there's a 0 heat flux, and the orange region receive a heat flux which is twice the average heat flux. So it's the most extreme case, let's say, you could study. And then they measure, so the velocity field from PIV, which are the arrows, and the colors represent the vorticity, the actual vorticity. And from left to right, they increase the Rayleigh number. And what you can see is that as you get more and more supercritical, you get this type of large-scale coherent structure that develop with counter-rotating vortices, so cyclone and anticyclone. And in between those vortices, you have this kind of narrow downwelling regions here. So again, they indicate that you can have this kind of large-scale coherent structures produced from this heterogeneity. However, they seem to observe that as the supercriticality is increased further, this becomes all looped, and you lose this kind of coherent structures at larger Rayleigh number, at larger supercriticalities.
Are these done with a flat top and bottom?
Yes, I think, yeah. Okay, so again, I'm not claiming here to do like a full review of everything that has been done with heterogeneous boundary conditions for rotating convection, but what I take from this is that, one, it has the potential to organize the convection at large scale, rotating convection at large scale. However, how robust this is at larger supercriticalities and smaller Ekman seems to be unclear, at least for the Earth outer core regime. So that's for the outer core. Now, if we think about the icy moons and Europa, there's fundamental differences which could make these conclusions different. One of them is the fact that for the outer core, we're really exploring or trying to achieve geostrophic regimes of rotating convection, rapidly rotating convection. For icy moons, we could be in a regime which is less constrained by rotation. So of course, this could have an impact on the effect of heterogeneities on the rotating convection. And the other important aspect, I think, is that the outer core is quite of a deep shell compared to icy moon oceans, which are really thin shells of radius ratio of about 0.8, 0.9. Yeah.
Was there any information on the time scale it takes, the information from the heterogeneities to reach the inner core, and how does it vary with different Ekman numbers?
I don't know on the top of my head. I would need to look at that again. I'm sure it has been estimated in some way, but yeah, I don't know. I need to look it up. So first of all, the amount of rotational constraint on the flow could be different, and the fact that it's a much thinner shell, you could think that the boundary, heterogeneity on the boundary could have a larger effect on the convection compared to a thick, deep shell, which is the case of the outer core. So going back to icy moons, has there been any studies looking at the effect of a heterogeneous pattern on convection, on circulation in icy moon oceans? Well, effectively, there was one study by Terranova and collaborators that was published almost at the same time as we published our study with Krista and Carver, which looked at the effect of heterogeneous heat flux for applications to Titan and Ganymede. So Titan and Ganymede are larger icy moons, and as mentioned by Krista yesterday, there is a high-pressure ice layer at the base of the ocean. And the heat flux that they impose in their simulations is basically taken from simulations of convection in high-pressure ice from Gaël-Choblet's simulations. And so what you would get from the convection in the ice would lead to rather small-scale heterogeneities. Okay? And so they use this as a boundary condition in rotating spherical shell simulations. What seems to come out of this study is the fact that this kind of small-scale pattern doesn't really affect the convection. It's not really able to change the properties of convection. What's an interesting point that they mention in their paper is that looking at the bottom boundary compared to the top boundary, it seems that large-scale patterns could be amplified. In particular, they mentioned that the pattern of order 2 is amplified from the bottom boundary to the top boundary. I thought that was an interesting point. But apart from that, it doesn't have like a big impact on the rotating convection, at least in the regimes that they investigate. You could think of doing similar studies for the case of Enceladus. So for Enceladus, again, Gaël-Choblet has published a study on what would be the heating pattern from the convection in the porous core of Enceladus. And you get these very narrow, kind of localized high heat flux regions. And it would be interesting also to look at how this could affect the convection. But again, these are rather small-scale heterogeneities. So from this study, it's not clear if this would really have the potential to affect the convection. So today, I'm interested in the case of Europa. And as I mentioned before, the picture is quite different because we're thinking really about the effect of a large-scale heterogeneous heat flux, which is closer to what is considered for the outer core dynamics. Okay, so to investigate this, we did a classical study by looking at rotating thermal convection in a spherical shell using the code MAGIC. We're looking at an ocean with a radius ratio 0.9, so it's a rather thin ocean. And we impose the heat flux at the bottom and the temperature at the top. We've also considered cases where we have both Dirichlet boundary conditions at both boundaries. Again, if we think about icy moon applications, of course, we neglect many important effects here. No tides, no libration, driven flows. We neglect salinity, and we neglect the phase change at the boundary. So this is only a first step to better understand what would be the circulation in these oceans. I can go quickly through this. It's been mentioned a lot of times already. So we solved the 3 governing equations, Navier-Stokes, conservation of energy, incompressibility. And we have 3 control parameters, plus another one, the Prandtl, the Ekman, and the Rayleigh number. And as Krista mentioned yesterday, if you look at the regime diagram, so here showing what Mike called the reduced Rayleigh as a function of the Ekman, with the different lines representing different scaling laws that allow to separate different regimes of rotating convection. You can try to, so going from rapidly rotating convection to non-rotating convection. You can try to estimate where these icy moons would fall. And if you do these estimates, they would fall annoyingly in this kind of transitional regime. In particular, Europa, Titan, and Ganymede would be less rotationally constrained than a moon like Enceladus. Of course, we can't do this in DNS, so we have to pick more moderate Ekman and Rayleigh numbers. It's not clear to me how we should do this. Should we rely on these scaling laws that separate, for instance, non-rotating and transitional regime to pick our DNS parameters? The problem with this is that you can see the lines of the constant convective Rossby numbers are not at all parallel to these scaling laws. So in the icy moon parameters, you could be in a transitional or non-rotating regime with a convective Rossby of 0.1. If you use the DNS parameters, if you're in the transitional regime, the Rossby number is of order 1. So I don't have if someone has a strong opinion on this and how we should pick the correct parameters to be in a regime that we think is relevant to icy moons, I'd be very happy to have yes.
Are we sure they are convectively unstable?
The icy moons?
Because you mentioned that you neglect any salt effect, but if you introduce back the salt, it could be stably stratified like our ocean, or is it?
I guess it could be stably stratified in salt. Would it be always, it would be in a double diffusive regime? I don't know, I haven't looked really at double diffusion. Do you have an idea, Krista?
I think it's hard to tell considering how little we know, but double diffusion is something that's been talked about.
I think in terms of the salinity and the stratification, we don't have any constraints, right, on what would be the stratification in the ocean. If you just focus on the thermally driven.
Yeah, low, but if you introduce salt back,
maybe.
You could have salt at the top as well.
Yes.
You don't really know. So
Yeah. Could destabilize it. Yeah.
So nothing is out of the question.
Yes, that's a paradise for fluid dynamicists. You can tell whatever you want. Yeah. But yeah, in terms of these, should I do simulations with the relevant convective Rossby number, or should I? What we did is relying on these scaling laws and picking simulation in the transitional regime, so not strongly constrained by rotation. Is this the relevant way the good way to do it, or should we rather rely on, I don't know, force balance and use the convective Rossby? I don't know if anyone has an idea.
You should fix that, the Rossby number, the real Rossby number.
The convective one, like the input?
The real one.
The output.
The output one.
Yeah, okay. Okay. So this assumes that, that we know, the speed in the,
Krista, do any of the new observations that we'll have for Clipper give us the flow velocities?
The most promising might be if you're able to detect some of the non-synchronous rotation, because if you're able to see some type of pulling of the ice shell, maybe you could get some constraints by that. That might be our best hope on that front.
So boundary conditions at best.
What about constraining salinity electromagnetically?
Yeah, that we should do.
Yeah, at what level?
There's a law with redundancies in the system.
I guess we don't know how deeply isolated it is.
Of the generosity.
So in a nutshell,
Our best hopes is actually combining all of the different observations we have to get some constraints on ice shell thickness, which then feeds back into the ocean salinity, Martin is mentioning.
Okay. Well, anyway, so what we did was, this. So what we did also was because we were, I think this stopped working. Okay, so basically because there's a big uncertainty in this, what I'm going to show today is mostly in a weakly rotating regime, but we've also considered simulations in a more rapidly rotating regime to kind of try to span different scenarios. We're far away from anything geostrophic. Does this work? Yes. Okay, so there's a fourth dimensionless parameter, Q star, so delta Q over the average imposed heat flux, which is the relative amplitude of the bottom anomaly. I varied this between 0 and 2, so 0 being homogeneous heat flux, 2 being kind of the extreme case where the heat flux is basically 0 here and twice Q naught at the poles. So we did this sweep in Q star. Again, Q star 0 is a homogeneous heat flux, so that would be your pure radiogenic heating scenario, and Q star of order 1 would be your pure tidal heating scenario. We increased that further, again, to go to the extreme case where this is 0. We consider 2 types of mechanical boundary conditions. Either the 2 boundaries are stress-free or the 2 boundaries are no-slip. The reason for this is that we're working at quite high Ekman number because we're working in thin shells, so the convective structures are quite small, and so it's challenging with this kind of high aspect ratio to go down to small Ekman numbers. So we might have an increased effect of Ekman boundary layers in these simulations. And because we're want to see the effect of the boundary heterogeneity, well, you can guess that the boundary condition could have a strong impact on this. So that's another uncertainty in this system. What type of mechanical boundary condition should we use in these simulations? You're going to see it's going to have a huge impact. So if we go for the stress-free cases first, I'm showing here, so the time average circulation, it's the mean circulation. The first row shows you the radial component of the velocity at mid-depth in the ocean, and the bottom one shows you the zonal winds. The azimuthal component of the velocity. So what you get is here what Krista published in the past in the case of a homogeneous heating scenario. So you have this upwelling at the equator, which leads to a higher heat flux at the equator. And you have these strong zonal winds, retrograde in the equatorial region and prograde at higher latitudes. So this is what I'm going to call the zonal winds solution in the following. And in terms of the effect of the heterogeneity, it just seems to basically modulate the intensity of the convection in this case. If you look at no-slip cases, this is what you get. So again, I'm showing the same radial and azimuthal component of the velocity, and you get a very different picture. So what you see is that as you increase the heterogeneity, there are 2 quite intense zones of downwelling that develop in the equatorial region, and 2 zones of broad upwelling. And you have a corresponding circulation if you look at the azimuthal component of the velocity. And this is what I call the thermal wind solution. And so if you remember what I discussed at the beginning of the presentation, you get radial geostrophic flows due to the azimuthal temperature gradients. So because here we have this order 2 pattern, you indeed expect that you will have 2 zones of downwellings and 2 zones of upwellings. And the fact that the upwellings are broader is also consistent with what was found by Dietrich in their simulations. And this is the kind of azimuthal circulation that you get that closes the loop. Okay, so this is what I call the thermal wind solution, which is very different from the zonal winds one. So if we accept that we have these 2 possible types of solution, the next question is to investigate how is the bottom heat flux anomaly transposed up to the isocean boundary in each of these solutions. So here I plot the imposed heat flux latitudinal profiles for the zonal wind solution and the thermal wind solution. And here I plot what you get at the top of the ocean, at the top boundary. So you can see that the anomaly is quite well reflected at the top of the ocean. You have this peak at the equator because of this equatorial upwelling. But other than that, you can see that it reflects quite well the anomaly. In particular, there is a transition between an equatorial cooling case to a case where the heat flux becomes higher at the pole. If you look at the longitudinal anomaly, the picture is very different. Of course, if you have the zonal wind solution, it's going to sweep out the anomalies in longitude. So they are strongly reduced. If you get the thermal wind solution, however, you get a good fraction of the anomaly that persists in this case. So to
what is the number?
Here it's 3 × 10⁻⁴. So it's quite large. And I'm going to mention later, we did few cases at smaller Ekman to see how robust that is. Yeah, so to quantify this a bit more, I'm just going to compute relative anomalies. So basically, peak-to-peak heat flux difference divided by the average heat flux. And I'm plotting here the anomaly in latitude at the top of the ocean versus at the bottom of the ocean. So if you're along the 1-by-1 line, it means that all your bottom anomaly is retrieved at the top. Okay? The colors represent different boundary conditions. So blue, both boundary conditions are Dirichlet, red, Newman boundary conditions. And then the dashed line is for no slip, and full lines are for stress-free boundary conditions. So in all of those cases, you see that the anomaly in latitude is well reflected upwards. You get it aligns along this one-to-one relationship. So the anomaly in latitude is efficiently transferred, and this might be consistent with what John mentioned yesterday, the fact that the dynamics at the poles seems to be behaving quite almost independently from what happens at the equator. There's some kind of regionalization of the convection, so if you impose a large-scale modulation in latitude, it will just be reflected upwards. If you look at the anomaly in longitude, of course, the picture is different. If you get the thermal wind solution, you get a good transfer of the anomaly in longitude. It's slightly reduced, but you get a good transfer of this anomaly. Of course, if you have the zonal wind solution, it's strongly reduced, in that case, down to 20% or so of the original anomaly you imposed at the bottom. Because this is a fluid dynamics audience, I wanted to mention this really nice observation that we made, which is in the case of Dirichlet stress-free boundary conditions, you can get a really abrupt transition from the zonal wind solution to the thermal wind solution. And this is illustrated at the top here. You start in the zonal wind solution, and as you increase Q star, or delta T star, because the temperature is imposed here, you suddenly transition from the thermal wind solution.
Is it hysteretic?
I haven't checked. I haven't checked.
Okay.
Yeah, because then we switch to Newman, and it doesn't happen when you impose the heat flux. So it's really surprising. I haven't investigated that in detail, but you can really see this zonal winds completely disappear, and you switch to that type of circulation. So that's something that could be interesting to look at for more, from a more fundamental perspective. This only happens in the weakly rotating regime. It doesn't happen in the rapidly rotating regime. We looked a little bit at smaller Ekman numbers to see how robust this was. So here, I'm plotting the relative anomaly in latitude, top divided by bottom boundary. So again, if it's equal to 1, you're reflecting all of your anomaly imposed at the bottom. Yeah, okay. There's a button here. Yes. And so as you reduce the Ekman number in those cases, it doesn't seem to affect much the efficiency of the transfer in terms of the latitudinal anomaly. So this seems to be quite robust, the fact that, yeah.
The Ekman number is based on the thickness of the ocean?
Yes, I think, yes.
What is the value for the planet? For the
10 to the minus, I need to look at the regime diagram, 11, minus 11, minus 12.
11, that's more, even on the thickness.
Yes. So we are far, very far. But it seems like, yeah, the behavior in latitude seems to be robust, at least for this small range of Ekman numbers.
After you have about 2 or 3 minutes.
Oh my goodness. Oh, okay. So it's not the case for the longitudinal anomaly. It decreases as you decrease the Ekman number. So it just seems to say that, yeah, as you go towards more planetary relevant regime, the anomaly in longitude could be erased at smaller Ekman numbers. So the latitudinal one seems to be robust, not the longitudinal one. Okay, we can now, how am I going to summarize this? We can try to, from this, make predictions for ice thicknesses. How long do I have? 1? It says 45 on my timer.
Okay, no, 3 more minutes here. We won't ask any questions at the end. We'll just look at you.
So yeah, we can try to make predictions for the ice thickness. I'm going to go past this. The caveat for this have been mentioned by Krista yesterday. We're missing a lot of physical processes, including the melting point depression with pressure that will change the temperature along the top boundary, salinity, possible double diffusion, processes within the ice, such as viscous relaxation and convective flows, and the feedback of the topography on the ocean flow. I wanted to describe a little bit the study that Krista mentioned yesterday, which is the first study where they actually couple the ocean dynamics with the dynamic ice formation using a phase field model. I'm just going to go straight to the conclusions. One important point that I get from this is that from their study, the topography of the ice doesn't seem to have a strong effect in terms of the latitudinal variations of the heat flux. So again, this is quite consistent with what I was describing earlier. They run a two-phase model, which is the blue line, thick, continuous blue line, and a monophasic model without ice, which is the green line. And basically, you get the same heat flux at the top of the ocean. So there's no feedback of the topography on the convection, at least in terms of the latitudinal heat flux difference. It's not the case for the longitudinal variations of the topography that could lock in convective patterns, especially if you imagine westward drifting wave patterns or convective patterns. The topography could lock them in a stationary position. So, to conclude, tidal heating, large-scale tidal heating could drive large-scale thermal winds in Europa's ocean. This is strongly dependent on the mechanical boundary condition considered, so I would say it's still an open question. The robust result is that in all cases, the latitudinal anomaly is transferred, so you get a regime that we call polar cooling in the community, so higher heat flux at the poles. It could induce longitudinal variations, but it seems like these could vanish at smaller Ekman numbers. There are many limitations in this study. We need to reach more extreme regimes of convection. There's this uncertainty about the rotational constraint that I mentioned, the effect and many effects relevant to icy moon oceans that we neglect. So I'll stop here and thank you for your attention.